Okay, so basically what we're doing here when we're converting it to a z-score is we're changing our unit of measure. Okay? And the reason why this is standard normal is because whether we're talking about centimeters of height or miles per hour or seconds in time or whatever, we are converting that unit of measure to standard deviations. Okay? And what this would allow us to do is if you think about the example we just saw in the video where we're talking about the heights of women. Alright, if we were going to classify people as short, medium height, or tall, you know, obviously we're not going to classify men the same as we would for women, okay? If you talk about a tall woman, you know, if a guy were that same height, we probably wouldn't necessarily call him tall, right? It's all based on what the mean height would be and the standard normal value. But what we could say is, hey, we're going to say that average height for a person is within one standard deviation of the mean, and then if you're below one standard deviation, we'll call you short, and if you're above one standard deviation, we'll call you tall. Okay? You know, we do this with IQ as well, but you know, you have your middle range, and then you have the other ranges on the outside. But with the heights, then we could classify people with the same categories based on their z value, not their actual height. Okay, because we'd have to deal with two different scales of measure, the female height and the male height. Whereas if we converted everyone to a z-score based on, okay, the guys, their mean and standard deviation, the girls, their mean and standard deviation, then, you know, we could have a guy and a girl who are two different heights in reality, but they both have a z-score of you know, negative 0.5. So relative to their gender, they're the same height. Does that make sense? It allows you to make comparisons when the original units of measure, or the original situation is not the same. Mm-hmm. Oh yeah, it is. Thanks. Now, if you take a look here, you do not need to know that probability distribution function, or probability density function, sorry. But notice it is similar to the one we had for the original normal distribution. It's just we have a z-squared in there now instead of any mu's or sigmas. Okay? Notice the notation here. He used that in the video. Z is distributed normally. And remember that first number is our mean. So the mean is always 0 in the standard normal distribution. Okay? And then remember the second number in here is always the variance. Okay? Now the nice thing is it's always going to be 1. The standard deviation is also 1. Okay? But then we have our formula here. Okay? X minus mu over sigma. The x minus mu part, all that does is it takes our bell curve and it shifts it down so that the peak is right at 0. That's the part, this x minus mu part, that's the part that makes the mean 0. Alright? Dividing by sigma is what converts all those scores to standard deviations. Okay? So this part shifts it so our mean is at 0. This part converts it to standard deviations. Alright? So that formula is up here again. Let's say I've got this data here. Okay? The mean of this is 21.8. The standard deviation is 2.9. Okay? So if I were finding a z value for 20, what would I do? Okay? 20 minus 21.8 divided by 2.9. Okay? So here's our x value, here's our z value. Okay? So that'd be a negative 1.8 over 2.9. And what does that come out to? Anyone have that?
Negative 0.62.
Okay, negative 0.62. Alright? Someone tell me why it's negative.
It's on the negative end of the.
Yeah, okay. Our mean originally was 21.8, right? So if we're shifting our mean down to 0 and our score is below the mean, then our z is going to end up below 0, right? So the sign is going to be important to pay attention to on these z-scores. Okay? So we could do the same thing for all of these. All right, 18 minus the mean over 2.9. We get a negative 3.8 over 2.9, and that's going to be negative what? 1.31. Okay? Now, this is where technology is nice because obviously we only have 5 here, so it wouldn't be a big deal to do all of them separately. But it is possible to do an entire list all at once, right? If we put these 5 pieces of data in a list, how could we find the z's for all of them at once?
Subtract 21.8 from all of them and then divide them all by 2.9.
Yeah, remember you can do operations on lists. So here I have my whole list of data. If I subtract the 21.8, by the way, if I found the mean right now, it would be 0. Okay, but we're not done yet. Now we're going to divide that by the 2.9. Okay? So there's our negative 0.62. There's our negative 1.31. The next one should be positive, and it is. So that's a positive 0.76. Okay. And then if we keep scrolling over, 1.45. And then a negative 0.28. Okay? So those are our z values. Again, using the technology to help you increase your efficiency is important. Okay? So, does everyone understand how to get the z score? No questions on that? All right. Now, one thing we can do with this, okay, let's suppose oh, got it here. Okay. Let's suppose that we know the standard deviation is 8 and a score of 50 has a z-score of 1.3. Okay? So we're doing a little bit different. We can actually use this to find out what the mean had to be. Okay? So we know the z is 1.3. What goes in for x? 50. We're trying to solve for mu. Okay? And sigma is 8. Okay? Yeah, multiply both sides by 8. And you get 10.4 That's 50 minus mu.
Line.
Okay. Yeah, subtract the 50 and then you'll divide both sides by -1 to get rid of the minus on the mu. And you get 39.6. Okay? So there's a case where you have a z value. You're able to use that then to find the mean. Or if you knew the mean but not the standard deviation, you could figure that out. Okay? That may even be a more likely situation where you know the mean but you don't know what the standard deviation was. Now, let's do like a little follow-up to this one. Okay. A little follow-up to this question. What score has a z equal to a -1.5? How might we figure this one out? Emily?
Plug in -1.5 for z, and then plug in 39.6, and using the formula, plug in 39.6 for the mean, and then divide by 8 and see what the x value and solve for x.
Yeah, okay. Z is -1.5. We don't know what x is this time, but we do know the mean now. It's 39.6. And we knew the standard deviation was 8. So now we can figure that out solving for x in this case. Okay? So you multiply by 8, -1.5 times 8 is a -12. That's x minus 39.6. Okay? So you add 39.6 to both sides, and x would equal 27.6. Okay? So that's another thing there. Once you know what that is, you can find the value that's a certain number of standard deviations away. Okay? So I know some of you might be tired, but let's try a little harder here. Okay? Alright, so now let's go back to this example here where we had this data, we got these z-scores, and I want to look at finding the probability. So we're going to look at this two different ways. This is what's called the standard normal table. You'll see a lot of variations of this, but the numbers inside will all be the same. Some of them will go down to negative, okay? In fact, I got a different one than I had first period because I didn't realize the one I had for first period started at -4 and only went up to a -0.3, so I was missing a lot of the values I needed. But let's look at how this table works. On this column, you have z values through the tenths. And you'll notice this one starts at 0 and goes up to 2.9. Okay? Across the top, we have the hundredths of a z-score. All right, so if we wanted, let's go with the 1.45 here. Okay, 1.45, we would come down to 1.4, and it's 5 hundredths, right? So we'd come over here, okay, and that would be the value from the standard normal table. Okay, so what does that mean? Well, what this means is that when we're finding a probability, okay, the probability that some random variable x is going to be less than or equal to 26 is going to be the same probability that the z-score is less than or equal to 1.45. Okay? Well, what probability is that? that's where this table comes in handy. We go to 1.45, and we have a 0.9265. So 92.7% if we rounded to the nearest tenth of a percent. Okay? So 92.7% of our data is going to be 26 or lower. Okay? And we do that by finding the z value. Now, so you might be saying, well, isn't this kind of what we did yesterday, but we didn't have to convert it to z's? And the answer is yes. Okay? But just trust me here. Okay? Because it's when we start working backwards that you'll kind of see the value in this. Okay? Yes?
So will we be given a chart like this, or are we going to have to find?
We're going to look at how to do it with our calculator, but I'm starting with the chart so you guys can kind of see where the z-scores come in handy. Now, I will say, in a lot of ways, using the chart is faster. It's just you're not going to be given the chart on your IB exam or anything, okay? But using the chart in a lot of ways is faster because you can just look, you don't have to punch stuff in. All right, so if I were doing number 24, okay? The value for 24. Alright, this goes with that. The value for 24, I want 0.76. So 0.7, 0.7, and then the 600ths. Okay. If I round to the nearest tenth of a percent, I've got a 77.6% chance that my score is 24 or below. Okay? All right. So does all this make sense? Okay. Now, the challenge with this table, and again, I told you every table, you'll find ones where they have the negative values on there. You'll find ones that only have negatives, or in this case, they only have positives. The challenge here is when we have these negative ones, and basically what you have to do, we want a negative 0.62, okay? Use the symmetry of the graph. So if you go to positive 0.62, 0.62 is right here, okay? How is below a negative 0.62 going to be similar to the positive 0.62? Amanda?
Maybe you subtract the percentage from 100 so it's like the opposite.
Exactly, okay? Rather than finding to the left of negative 0.62, we just find to the right of positive 0.62. Okay? So we subtract 100 minus 73.2%, and we would get, not 80, 26.8%. Okay? So, good. We're using the symmetry of this standard normal distribution. Okay? Alright, so does anyone have any questions about this? Okay. Now, where the table is nice, and this is getting to what we're going to focus on tomorrow, but tomorrow we're going to look at things where, okay, so what would my score have to be in order to be in the top 80%? Okay? That means I'm in the 80th percentile, or my score is at or above 80% of the rest of the people. Okay? Well, what I would do is I would come over here and find 0.8. Okay? 0.84. That's the closest. Okay? Yeah, this is a little closer. So we would say 0.84 is going to be our z. Okay? Well, now, if we go back and we use our mean and our standard deviation we had before, okay, 21.8 and 2.9, okay, x minus 21.8 over 2.9 is going to equal 0.84. Okay, and you guys can figure that out, right? That's where the calculator is actually really helpful, because notice we had to kind of settle for something really close, right? Whereas our calculator is going to help us get exact ones, right? But we'll look at that tomorrow. I just wanted to show you that how this all relates to the table. It's really a nice tool, and in some ways it's even more useful than the calculator is. Okay, but let's talk about doing this on the calculator. All right, some people were questioning, you know, why do we have to convert them to z's if our calculator was able to find it for the original values? Okay, well, if all we're ever going to do is find these probabilities, we really don't have to convert them to z's. All right, but as we'll see as we move forward, we are gonna need the z's later, especially so. It's helpful to practice with them with this, and also in some ways it does make it a little easier. We're going to use the normal CDF function on our calculators like we did the other day to find probabilities. Okay, so let's say that first of all we want to find the probability that a random variable x is less than 20. Okay? Now, because we know the original data, we know the mean was 21.8, we know sigma was, what was it, 2.8? 2.9, okay? We could use this and plug in 21.8 and 2.9, okay? And the upper bound would be 20, and the lower bound, in this case, 0 would be a good lower bound, okay? But one of the challenges we ran into the other day was making sure that our lower bound was low enough or our upper bound was high enough. Okay? And this is one thing that using our z's actually makes simpler. Okay? So while this will give us the right answer, we could translate this into, hey, if I'm looking for the probability that a random variable is less than 20, I'm really finding the probability that the z is less than a negative 0.62, right? And the nice thing about this is when I do the normal CDF on the calculator, okay, remember my units are standard deviations. So how many standard deviations did we say you wanted to go down in order to ensure that you had all the data you needed? What do we say? Like 3 or 4, maybe even 5? Well, guess what you plug in here for your lower bound? A -3 or -4 or -5. Okay? I'll just do -5, make sure. But you don't have to think too hard when you're figuring out your boundaries. If you want to go less than a value, you pick -5. That's 5 standard deviations down. Okay? So then our upper bound is the negative 0.62. Okay? So we punch that in. Negative 0.62. 0.62. Alright? And then remember the mean and the standard deviation is what this takes. Well, we're doing a standard normal distribution. So it's always going to be 0 and 1. Okay? Now, I know some of you weren't here, so let's review how to do this on our calculators. Okay? If you recall, it was under distributions, which is above the variables key. Okay? So second distribution. And it wants to reopen. So second distribution, the very first one there is normal PDF. Remember, that's what we use to graph these, so we don't want that one. The second one, normal CDF. So what we're going to use, and we type in a negative, oh, that doesn't do negative, a negative 5, a negative 0.62, and then 0 and 1. Okay? And we get 0.268. All right, so 26.8%. All right, which, if you look back, that's what we got from our table as well. Okay, but we can use our calculator instead of the table. All right. Does anyone have any questions about how we did that? Yeah, Charlie?
Why is the upper bound negative 0.62?
Because we want z to be less than the negative 0.62. So we're going from negative infinity up to negative 0.62. All right. If we were looking at this on a bell curve, okay, if this is our z, our mean is at 0, we're at negative 0.62, so we're finding that area. Okay? So we've got to go to negative infinity. That's why we put a -5, because that's 5 standard deviations down, up to a negative 0.62. Okay? All right, let's try a couple others here. Good. Let's say I wanted to find the probability that our score was greater than 24. Okay? How would I do that? In terms of z, I'm finding the probability that, yeah, I'm finding the probability that z is greater than 0.76. Okay? So how am I going to do that?
So you do normal CDF, and then would your lower bound be 0.76?
Mm-hmm.
And then you could just make your upper bound a big number, like 100.
You could make it 100, or, I mean, that would be 100 standard deviations, so we could even just use 5 or something. That would be 5 standard deviations. 100 is fine, and that's the thing. I mean, whether you use 5 or 100, it really doesn't matter.
I
So
don't understand how you're getting that
5 standard deviations.
Okay.
Because it's a bell curve. Remember when we talked? Well, part of it is. Were you here Monday? No. Okay. Watch the video for Monday, because once you get past 3 standard deviations, all of this data out here only accounts for 1/4 of 1%.
Okay.
So if we went out 5 standard deviations, it would be so minuscule when we're rounding to the nearest 1/10%, it's not going to make a difference in our answer.
So that's why it wouldn't matter if you use like 5 or 100.
5 or 100, yeah.
Okay.
So whether you go out 5 standard deviations or 100, you're talking at that point about 0.010% or something like that. So, all right. So we use that again. We use 0 and 1. Okay. Now this one is a greater than problem. So how do we do the greater than part? Oh wait, I'm sorry. That will give it to us. Okay. I was thinking table again. So what do we get when we do that?
22.362.
What is it?
22.362.
22.362. So 22.4%. Okay. Now, if you had done it like this, from -5 up to 0.76, you just have to subtract from 100%. Okay, use that complement idea. Alright. So. Alright. This is a little bit of a preview of what we're doing tomorrow. Okay? Suppose you know there's a 20% chance of having a score below 30 and the mean of our data is 42. Okay? Find the standard deviation. So here we know the mean, we know the probability, we don't know the standard deviation of our original data. Okay? So if we go back to our table, okay, z equals a negative 0.84. Well, we would have to go to a positive 0.84. Okay. Since 20% is not on our table here. Okay. 20% isn't on here, so it's obviously in the negatives, which makes sense because it's less than 50%. So think about the complement. If we want the bottom 20%, it's going to be negative whatever the z-score of the top 20% would be. So we're looking at 80 again. So there's 80, that's at 0.84, so the bottom 20% is going to be below negative 0.84. Okay? So that's where we got this value here. Okay? So now if we're finding the standard deviation, we can plug that into our formula, okay? Negative 0.84 equals the score.
32 or 30 minus 42.
Yeah, the score is 30 minus 42. What's the standard deviation? We don't know. Okay? So you just leave the sigma in there. So now negative 0.84 sigma equals a negative 12. Divide by the negative 0.84, and what do you get for sigma? Should be
14.28.
Okay. So that's going to be the standard deviation for our data. All right. We'll look at how to do that, how to find that z with the calculator tomorrow.